resonance. Again, a resonance is you can detect a resonance if in the frequency domain, frequency space, the response of the system has a peak. Whatever this is, pero parang may nagpi-peak. Yan, ganyan. So this is a resonance peak. Okay. In the fundamental sense, this happens when you have a signal that is, or rather a system that may have second or higher degree order. So whatever the system is, this could be your sound box, all right? So you input a sound to the sound box and it also vibrates, so that's the output. The function that describes the sound box, G of S, and S is in Laplace transform, no? This could be because if it resonates, this could have second order or higher components or higher order components. But the second order is the basis of that. Okay. Now why so? What is a general second order system? That's G of S. Okay. A second order system in general would have a transfer function of the form S squared 2 zeta omega n S plus omega n squared under omega n squared. Okay. So anything with this form would have a second order. Again, omega n is the natural frequency. But this is if it's without any damping. Okay. Whereas zeta is the damping coefficient. When we're talking about the frequency response of a system, starting from the G of S, again, di ba, S is a complex frequency. So it has exponential and radial components, complex, no? Now, yan. Now, the thing is, how do we get the frequency response from this equation? Well, remember, if a system is excited, it will undergo a transient response and then finally go to a steady state. When a system is subjected to a sinusoidal signal as input, okay, remember please that magkakaroon siya ng transient response and eventually mag-i-steady state. How does a transient response look like kapag sinusoid yung ini-enter mo? Well, at the start of the excitation, parang medyo, kunyari, ito yung original signal, medyo pwede siyang hindi pa masyadong in sync with the sinusoid. So that's why you know it's a transient response. It is found at the start. If you trace it relative to the input signal, it doesn't really match very well. However, after a time, kikita mo na pareho na sila ng shape. So you're certain that this is already the steady state. So how do we isolate the steady state response in a sinusoidal input and output? Ang gagawin natin is we will assume S. So again, to get frequency response, no? Let S just be equal to J omega. So kumbaga, tinanggal na natin yung effect ng ng exponential frequency because this one is related to the transient response. Remember, when we get the solution of a Laplace transform product input-output, usually, ang kalalabasan is there's an exponential function and itong S na to, siya yung kung ano man yung result ng S, value ng S na tinitignan natin, siya yung pupunta as an argument to the E. So, pag ilagay natin yung S, di ba nga, ganyan yan. Ayan yung S times T. And remember, usually may minus sign. Depende sa, kung stable yung system, usually the real part is a minus sign. So the imaginary part, okay lang yan kung plus or minus, doesn't matter. But what would happen if there's an minus sign there, is you have e to the minus sigma t, e to the minus j omega t. And we know this is a sine and a cosine. Minus I sine omega t. This part is the vibration part. But this one, e to the minus sigma t, this is just the envelope.
Multiplying the two together results in vibration which is enveloped by an exponential function. The first term, eh, after a long while, will vanish. This first term is responsible for the transient response. So for different input functions or forcing functions, the transient response appears as at the start of the a excitation, some wiggle before the system output copies the input. So you can see it from a ramp, or you can see it in the sinusoidal signal. There would be a little bit of wiggle before the output tries to follow the input signal. Get the frequency response given the transfer function, we substitute S only by j omega because the term where sigma appears will in the steady state vanish. So substituting j omega in a second order transfer function, we get this function. And as you can see, the denominator has a complex or rather imaginary term. We need to rewrite this in a real plus imaginary term. And therefore, what we do is we multiply this function by 1, where 1 is the conjugate of the denominator over itself. carrying out the operation, we see something familiar, difference of squares, and so substituting, we get this term. Finally, we are able to write the equation as a separate real plus imaginary part as shown here.
Okay? So, anong gagawin natin para makuha natin yung frequency response? Ito na yon. Except that, remember, kapag sinusoid ang pumasok sa signal, depende yan sa frequency. Look here, now it is a function of omega. Diba? The omega is there, the omega is there. So, enter a value of omega and plug in mo dyan, and then makaka-plot ka for a range of omega, mapaplot mo na ngayon yung real and imaginary part. Now, the frequency response is actually displayed in two graphs. Displayed as what is known as a Bode plot. Okay? The Fourier spectrum is just like a Bode plot. The one is the gain plot, and the other is the phase plot. Okay? This is expressed in omega in log scale. Bakit log scale? Kasi nga, kapag frequency response, masyadong mahaba yung range. Tingnan mo, sa atin, 20 Hz to 20,000 Hz. I-display mo yan as linear. Aba, that means you have order of 10,000 points. Hindi ganon. But if in log scale, you go from 20 or order of 10, order of 100, order of 1,000, order of 10,000. So it's manageable. Once again, the frequency is in log scale because of the wide range of frequencies that can be subjected to the system. That's why all frequencies typically are in log scale for frequency response. The phase plot, bakit nga ba phase plot? And bakit gain plot? The gain plot is kung ano yung nangyayari dun sa amplitude na lumalabas doon sa system. It's a ratio of the input amplitude and the output amplitude. So that's why gain. All right? And once again, this is displayed in dB. So kapag may imaginary number ka, 'di ba? C is equal to x plus iy. Para yang para yang this is the real part, this is the imaginary part. Parang yung x mo is the real part, y mo is the imaginary part, and that point there is your z. Right? So, yung magnitude is essentially the length of that phasor. So nga in fact ang tawag nga dito vector in complex space is a phasor, no? Na gumagalaw in time. So the magnitude of C is equal to the square root of the real part plus the imaginary part. So ganun din sa gain. Pag kinuha mo yung gain, kukunin mo yung frequency response imaginary part and real part, square mo sila, kukunin mo yung square root. And then, this is typically a ratio. I-transfer function na to, no? So, ratio of input and output na to. So, you're gonna multiply that by, so essentially, ayun yung G, no? 20 of log of this gain. Puno ka doon, girl. Yan. 20 times the log of this times a decibel unit. Okay. So once again, it is displayed as decibel and log scale. And when you're talking about volume, again, the log scale is used when you're talking about volume of sound. So ganito yung pag-display sa kanya. So this is in dB scale. Okay? Whereas the phase plot naman, di ba? Itong angle na to, parang tangent yan, ano? Tangent of y over c. X. Diba? And that's the phase plot. So, no, that's the tangent. Arctangent pala. Wait, sorry. I'm sorry. The angle, the tangent of the angle, okay, for a phasor is the imaginary part over the real part. And therefore, the angle itself is the arctangent of that. Now, if you display it in angles, no, then sa phase plot, dinidisplay yan as 0 all the way to minus 180 degrees. Okay. Whereas yung dB, when you have 0 dB, it means pareho yung amplitude ng input mo at output mo. And when you're getting lower dBs, ibig sabihin, in log scale, bumababa yung amplitude ng signal mo. Now, you have this function. You know the real part and you know the imaginary part. Therefore, you can calculate the magnitude. Okay? You can get a function for the magnitude and you can log that. This function is a function of omega, which you can input. For example, you want to go from 20 hertz, then you plot it up all the way to 20,000 hertz. Yeah, you can do even in Excel, you can do that, right? Now, if you do it for this equation, I don't need to show you, but you can do it on your own because we only have 10 minutes. For a second order system, the body plot of the gain of the second order system looks like this. For up to a certain frequency, 0 yung gain. So, ibig sabihin, walang nangyayari doon sa amplitude, hindi niya napapalitan. But, there is a certain frequency, we will call that WD, where it will peak. After that frequency, it will decay. And the rate of decay of the amplitude is, as a function of frequency, is 40 minus 40 decibels per decade. The decade means a step of 10. Okay? 40 decibels, a step of order of 10. And this, my friends, is what is the resonance peak. Ibig sabihin, second order systems can possibly have an output amplitude which is greater than the input. at the resonance condition. The resonance peak is equal to omega n 1 minus zeta. Yan. Yan. There. And this is the origin of the resonance. So, ibig sabihin, if your system may have a complicated G, or we don't know its G at all, but the resonance only appears if the system is second order or higher. So we are certain if we find the resonance peak in the frequency response of your system, it certainly has a second order there somewhere. There. End of story. The phase plots would look something like this. Up to a certain frequency, okay, zero phase shift, but eventually, nagkakaroon ng phase shift, and eventually, 180 degrees na yung phase shift. So, totally opposite na yung phase shift at, 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 at certain frequencies, time frequencies. Okay? All right. Okay. Is that clear? This is just a rough description of why there is a resonance, why there could be a resonance. And the short story, the second order systems have, depending on the settings of zeta and omega n, will actually have a resonance peak. Okay, that's it. Any questions about today's lessons? I'll stop sharing from this side. Stop sharing. Stop. May tanong ba tungkol dito? Waiting. Wala. That's it. That's all for today. And I'll see you, if there are no more questions, I'll see you on Wednesday, December 22, 10 o'clock. Please bring your Arduino. Make sure the motor is there, and we will play with the motors and try and move things. Okay? So, thank you for your time, and I'll see you Wednesday. Bye. Bye all.